Thank you very much for the invitation and for the provocative introduction. So, I will show that this FDR, that means four-dimensional regularization or renormalization method, is more convenient than dimensional regularization because of the following reasons. It is four-dimensional. This is always good for numerical methods if you want to compute things numerically, and it's also good for SUSY because you know that in SUSY there are the fermionic degrees of freedom, the bosonic degrees of freedom that don't match in normal dimensional regularization, while here, since it is four-dimensional, the method, there is no problem for SUSY. Order-by-order renormalization is avoided in FDR. There is a leftover finite renormalization that is required just to fix the parameter of the theory in terms of the experimental observable. This is the only meaning of renormalization in this framework, fixing the theory in terms of observables. Then there are some technical advantages. L-loop integrals can be reused directly in L+1 loop calculations with no need of further expanding in epsilon as you would do in dimensional regularization. You can treat in the same four-dimensional framework also collinear and infrared divergences. And then you can interpret non-renormalizable field theories in such a way that you can actually restore predictivity in the infinite loop limit. So, this is the outline of the talk. I will tell you a few words about the FDR idea. Then I will give a physical interpretation of the idea. Then the bottom-up approach, what I call bottom-up approach, I mean that I use this FDR approach in order to reproduce known result that you can also actually obtain in dimensional regularization. This is actually a consistency check that this approach actually reproduces whatever should be reproduced in the renormalizable quantum field theories. And then the last part of the talk I will speak about what I call top-down approach. I mean the interpretation that you can give to non-renormalizable quantum field theories, just copying somehow what you can do in renormalizable quantum field theory with some extra information that you get, that you learn from FDR. So what is FDR? It's a four-dimensional regularization / renormalization approach. The idea is very simple. You encode the subtraction of the ultraviolet infinities directly in the definition of the loop integral. You don't touch the Lagrangian, you just define a different kind of loop integral, such a way that it is finite and fulfills all the properties that you need. This is a list of the papers that have been written from the first paper up to the last two-loop calculation that I performed with a student of mine. So, let me start with this idea. Take the integrand of a loop function. In the rest of the talk, whenever you see Q1, Q2, QL, they are all integration momenta. So just take the integrand of a loop point function in the momentum space. And let's imagine that you can divide this in an infinite part plus a finite part. J-inf is the infinite part, and the finite part is this. The finite part is defined to be the integral such that it is integrable in four dimensions. It means that the integral, after integration, you would get some ultraviolet infinities in terms of 1 over epsilon pole if you use, for example, dimensional regularization. We will see in a moment that while doing this separation, you generate spurious infrared divergences that I have to take care of. In order to deal with them, I interpret the plus I0 prescription that is seated in the denominator like a kind of mu square mass that I call minus mu square. So, and I take the limit mu square equal to 0 outside integration. This is not like dimensional regularization. In dimensional regularization, the I0 prescription tells you that inside the integration, before integrating, you have to take this epsilon equal to 0. While now I'm taking this outside, so I'm interchanging the limit. I'm just changing the definition. So as a matter of definition, I can define whatever I want. So this is just a definition that I'm giving. So how I do perform the split? I split this integral in such a way that the infinite part of it, the part that would give rise to uv infinities upon integration, is allowed to depend only on mu, not on physical scales. So in this sense, all physics is just in the finite part. Then the FDR integral over the original integrand that I denote with this symbol, where I use these square brackets in the D4 Q1, Q2, QL integration, is defined to be the limit mu equal to 0, and this is just the I0 prescription outside integration, over the finite part only, that by construction you can integrate in 4 dimensions. It's just like throwing away completely the infinite part. Excuse me? It is Minkowskian. You can always recrotate to the Euclidean. Okay, so it is irrelevant if it is Euclidean or Minkowskian at this level. So the important point is to better define what is the separation between the infinite part and the finite part. So in order to clarify this, let me give you a concrete example. This is a rank 2 tensor of a 2-loop function. So I just start with a 2-loop function. That depends on momentum Q1 and Q2. Q1 and Q2 are the integration momenta, and this is the integrand of the function that I want to integrate. And you can draw the diagram. Well, can I write here? It would be something like you have a propagator Q1, you have Q2, Q12, and for example, by using Feynman parameter, you end up with having this propagator to the 3rd power, and then in addition you have some numerator structure with Q1 mu, Q1 nu upstairs, something like this. To externalize, for example, well, in QED, something that generates some momentum here. Okay, this can be a diagram, an integral that occurs, and then D1, D2, and D12 are just propagators. We have 3 propagators that brings Q1, propagator that brings Q2, and propagator that brings Q12. The integration over this is the momentum, the integration momentum is Q12, that is Q1 plus Q2. And there you see that I use this bar notation. This bar notation means that I am taking seriously this plus I0 prescription. So I'm just somehow including this mu square in all propagators. So this is the reason why I put this bar in these denominators. And I also define Q bar square like the original Q square minus mu square. Excuse me? No, you can actually say that mu square is minus I epsilon. You can do it. There is nothing wrong in taking this to be really I epsilon. But for, it's better for me to call it mu square. Then you can actually apply those 2 identities, and you can rewrite, this is an identity, you write 1 over dj, like this, and then you see that the first term is actually doesn't depend on any physical scale. The physical scale are just m1, m2, and m12. They are supposed to be masses, internal masses, so they are physical. But this qj squared only depends on mu square. So there is no physical scale, just the mu square scale here. And the second term is less UV divergent because you have 2 denominators upstairs. It's going like 1 over qj to the 4th. And then this is another identity that you can use in order to disentangle subdivergences. And then you can rewrite an identity. You can rewrite the initial integrand like this. Again, this is just an identity. And you see that you are able now to disentangle those terms between brackets, square brackets that I write in brown, that are the terms that give you the UV divergency. So they are actually, by cover counting, you can see that they would be divergent upon integration, and then some terms that are written in black that doesn't give you any problem. So you can in these brown terms are both. This is globally divergent when Q1 and Q2 go to infinity, while this other term, this multiplied by this, is only divergent when Q2 goes to infinity. And this is multiplied by something that is finite, but is still divergent, since that is giving you some divergences. So what I do, I drop it to be more complete. This is my original integral, and the infinite part of this is defined to be anything it's proportional to something that is brown, while the finite part is all the rest. So this is the separation between the two pieces. And the FDR integral over the original integral, this is the original integral, is the limit of mu equal to 0 of the finite part only. That I rewrite, because I will need it later on, as a Q1 alpha, Q1 beta times this parenthesis. And this parenthesis is actually referring to the denominator expansion that I had to do in front of Q1 alpha, Q1 beta in order to extract the infinite part from the integrand. So in a sense, the only thing that I'm doing is just expanding denominators, while the Q1 alpha, Q1 beta term that was present from the very beginning stays there. So I'm just expanding denominators that are multiplying Q alpha and Q beta in such a way that what is left I can integrate in 4 dimensions. So and this is this purple parenthesis is actually the expansion that I have to do in order to get this separation that is equivalent to what is written here. It is unique up to a shift, in the sense that, of course, I have to be, the separation shouldn't depend where I put Q1, Q2, or Q1, 2, or if I put Q2 plus an arbitrary momentum, but one can show that after integration, whatever separation you do, you end up with the same integral. Okay, so in a sense, the separation at the integrand level is not unique, but you can show that after integration, you always get the same result. So, formal properties of the definition. One can show that shift invariance is guaranteed, in the sense that, as I told you, you can start with an integral that depends on Q, and then make this Q go into Q plus P, where P is arbitrary momentum, and then this operation that is actually allowed in convergent integral is always also allowed for this would-be divergent integral. And then you can keep simplification between numerators and denominators that are the only two properties that you need in order to guarantee gauge invariance. If you think about gauge invariance as a formal, if you think of proving gauge invariance by actual computation, meaning that you can prove word identities or Slavno-Tyler identities diagrammatically, the only properties that you need in order to prove these identities that you can simplify numerators with denominators when you can reconstruct denominators upstairs. And then you can show that this kind of definition fulfills this requirement, so it is compatible with gauge invariance. To prove property 1, it is enough to note that this FDR integral can also be thought as a difference of the original integral the difference between an integral, a dimensional regulated integral over the initial, the original integral minus the dimensional regulated integral over the infinite part that I'm subtracting. This is nothing but JF that I rewrite like the difference between the original integral and the subtracted part. And since those two terms are invariant by shift, this also tells you that my definition is invariant by shift. I have some backup slides later on if you want to go into detail. But okay, in this case, it's very convenient to use dimensional regularization, but actually the two integrals could be regularized by any means, because by definition the difference doesn't depend on the way you decide to regulate the two integrals. So, and then as I told you, you can simplify numerator with denominators. And this is something that you have to do in order to prove word identities diagrammatically. For example, you would like that if you have an expression like this, you can simplify this Q1 with these denominators and to write a resulting expression in terms like this. And this is actually something that is crucial in order to prove the gauge invariance. And then you can do this just defining, while modifying the denominators, you also have to modify any self-contracted momentum square appearing in the numerator in the same way you are deforming the propagator, in the sense that you should somehow also include the plus I0 prescription upstairs when you want to cancel denominator and numerators. And in order to do this, you should define somehow an integral over this I epsilon appearing upstairs in such a way that you need in front of this mu square the same denominator expansion you would do in front of Q1 square. This is quite technical, but the message here is that you can force the numerical, the cancellation between numerator and denominator in such a way that you can fulfill gauge invariance. And then there is also a definition that is a corollary of this treatment. Then also irreducible tensor can be defined like this, and since everything is in 4 dimensions, you can, at the integrand level, instead of Q1 alpha, Q1 beta, write G alpha beta divided by 4 Q1 squared. In dimensional regularization, you would have G alpha beta divided by n, but since everything is in 4 dimensions, you can write this integral like that, and then if you want, you can reconstruct the denominators, but then you have to pay the price of having this extra piece that is an important constant that you have to have in order to get the right result. This is related with gauge invariance as well. So, it is important to study the dependence on mu. Mu is this plus I0 prescription, or this plus I epsilon, as I called it sometimes. So how this FDR integral depends on this mu. Mu is a kind of unphysical scale that I'm actually including in order to deal with the infrared divergences that I get when I make the splitting. The fact that I get infrared divergences when I get the splitting is actually, you can see from here, because when I split this, I get something propagator Q2 to the 4, for example, and this is actually giving rise to infrared divergences that are regulated by this mu square. Of course, if I put everything together, I don't have infrared divergences anymore if I start from an integral that doesn't have infrared divergences. But the fact that I'm actually getting rid of one part of the integrand is actually causing the appearance of spurious infrared divergences. So now I'm studying how this expression depends on this mu. Okay, I rewrite this FDR integral as a difference of dimensionally regulated integrals, and I study the right-hand part of this equation. This first term doesn't depend on mu, because this is nothing but the dimensional regulated version of the original over the original integrand. So if I assume that J doesn't develop infrared on collinear divergences, I can take the limit mu equal to 0 inside the integration. So this piece doesn't depend on mu. Now I'm studying the integral over the infinite part of it, that is the UV, it is the integrands that cure the UV divergences of the original integrand. Of course, I can have several types of divergences. I can have here some integrands that are polynomially divergent, or some integrands that are logarithmically divergent. As far as the polynomially divergent integrands, once I integrate over them, I get always something that since mu is the only relevant scale. If I start from a polynomial divergent integral, I would always get polynomial in mu from the polynomial divergent integrants sitting here. But since I'm taking the limit mu equal to 0, they wouldn't give me any contribution. So the only possible terms giving me a contribution as far as the mu dependence is concerned are the logarithmic divergent integrants in J-inf, because if I perform the integral in dimensional regularization of these subtracted integrants, I would get a logarithm of mu divided by mu r, where mu r is the normal arbitrary scale one has in dimensional regularization. So then, since I have only logarithm of mu coming from what I told you now on the right part of the equation, it means that also on the left part of the equation, I have just a logarithmic dependence on mu. And so it tells you that this object is only logarithmic dependent on mu. And then I can do some other thing, because actually there is a limit mu equal to 0 that I cannot take because I have a logarithm of mu appearing here, so the logarithm of 0 doesn't exist. But what I can do is just to take this logarithm that appears here and put it in the left part of the equation. And this logarithm of mu would always bring the logarithm of the renormalization scale as well, because the logarithm should be a logarithm of a dimensional quantity. So whenever I have a logarithm, I have a minus logarithm of mu r. So I take this logarithm, I put on the other side of the equation, then I take the limit mu equal to 0, in the sense that the logarithm of mu appearing here cancels with the logarithm of mu that appears here, and then what is left is logarithm of mu r. So in this case, by doing so, I can actually take the formal limit mu equal to 0 by trading logarithm of mu with mu r. So I don't have a logarithm of mu in my integral anymore. I have a logarithm with mu bounded to be a small number because the limit mu equal to 0. But now I traded this logarithm of mu by a logarithm of an arbitrary scale mu r. So in this sense, with this definition and with this trick of moving this logarithm in the definition of the FDR integral, the integral doesn't depend on any cutoff anymore, but depends on the renormalization scale mu r only. So let me give you an example by using not dimensional regularization, but another regulator, because the argument is the same. This is my original integral. This is a one-loop example. This is a two-point function, one propagator and the other propagator. And I can extract the infinite part of it like this, plus a finite part. The finite part is, in this case, defined just as a difference of this minus that. And then the logarithm that appears, that I was speaking before, is only coming from the integral over this divergent part. Now I'm taking a cutoff regulator, lambda, and by computing this integral, I have to compute the limit of mu equal to 0 of this integral regulated by lambda. And then I cannot throw everything away, because if I throw everything away, a logarithm would pop up here, a logarithm of mu, because I'm just taking care of one part of the integral and just forgetting one part of the integral, and I cannot do it. So what I can do is to split the integration region in an arbitrary way between 0 and mu r, where mu r is an arbitrary scale, and mu r and lambda. So, and then I throw away all these integrals and also the constant term coming from the other. So I'm left over with this logarithm of mu that I can put on the other side of the equation. And now I can simplify the logarithm of mu, and the only thing that is left over is a logarithm of mu r. And so this mu r in this language of cutoff renormalization is just an arbitrary separation scale between the infrared and the ultraviolet regime. So in a sense, I would like to throw away also logarithmic infinities, but I cannot throw them away for free. What is left over is a logarithmic dependence on mu, but if I take this logarithm to the finite part, I can trade this by a logarithm for a logarithm of renormalization scale. So this is actually the result of this integral once I have taken care of the logarithm in the way I told you. And this is, for example, what I get for the FDR integral. And this is just nothing but the normal expression what would get in dimensional regularization once you throw the pole away. So this is actually nothing but the MS bar scheme in dimensional regularization, except that I got rid of the infinities before integration. Okay, so yes. Those are fake IR divergences, in the sense that I'm assuming for the moment that my original integral is infrared safe. Okay, then this mu is only coming from these fake infrared divergences that I'm coming because I'm not taking all the integrals. Then this symbol means that I use partial fraction identities in order to separate divergent integrals from finite integrals, and I take care of this cancellation between numerators and denominators in the way I try to explain you. Then I drop all divergent vacuum terms from the integral. I integrate over d4q, the finite part. I take mu equal to 0 until I get a logarithmic dependence that I know that is the only dependence that I can get after throwing these infinities, until I get this logarithmic dependence, and then I compute the result in mu equal mu r. And then in this sense, mu equal mu r can be embedded in the definition of this integral. So this is the formal definition of FDR integral. So,
you said the integral didn't depend on physical parameters, but I wasn't quite sure what you mean by physical parameters.
well, in this example that I gave it to you, means that all this brown square bracket inside, they don't depend of any mass, external or internal. They are just the integration momenta square minus this mu square.
In the previous example,
Yes. Here. So here there is an infinite part that is multiplied by something that is fine. Then in this case, if, maybe it is a prescription, but I throw it away anyway.
But that whole term will depend on the physical.
Yes, this is, well, yeah, in a sense, if you have it in dimensional regularization, you would have something like 1 over epsilon coming from one integration times, you know, some finite integral on the other variable. So this is anyway a pole that you throw away in dimensional regularization anyway. So the prescription, if you want to call it a prescription, is to throw all these kind of integrals as well. So it is enough that one of the integration is put in the form of not having inside any physical scale. This is the definition. If you want, this is part of the definition. I don't have a better explanation. This is part of the definition. So physical interpretation, you have a bunch of quantum field theories at a certain scale, and you want to see if these theories survive when you increase the energy. And when you increase the energy and you do loop corrections, you generate logarithm of the ultraviolet cutoff, or even powers of the cutoff. So the idea is to consider this dependence on the cutoff unphysical in the limit of the cutoff going to infinity. It's a kind of modern version of ether. So the idea is just I try to ignore them and to see whether whatever is left after ignoring them has anyway good properties that allows me to perform calculation. So in a sense, I don't care how these infinities go. I just concentrate on what is left and on the consequence of actually forgetting about infinities. This is the philosophy. So the point is that not where to put the infinities. For example, I'm not thinking about putting infinities in the Lagrangian. I'm just speaking about what is the cost of throwing away infinities. So there is no cost for polynomially divergent infinities that I call decoupling in this framework, because polynomial divergent infinities would always, in this framework, manifest themselves in terms of powers of mu square. And since I take in the limit mu square equal to 0, they don't contribute. They don't have any effect on the physical part. So the only cost that I have to pay is that I cannot throw away for free logarithmic infinities, because I generate this logarithm of mu that actually brings me some dependence on the renormalization scale in my physical part. So the only cost is coming from logarithmic infinities, because an arbitrary scale that I identify with the renormalization scale pops up in the physical observables. And now I want to be provocative. The physics of the ultraviolet scale manifests itself only logarithmically, at least in this framework. Then I can compute the logarithm of mass of the Higgs and logarithm of the Planck mass, and those two numbers are not really, really difficult. I mean, really, really different. So in the sense that this just tells you that if I consider the quadratic infinity to be unphysical, there is no hierarchy problem, because everything is logarithmic, okay? This is provocative. So can I do something better? Can I classify the things that I'm throwing away? This is a classification that I can give independently on the number of external legs. At one loop, this is actually the only logarithmic integrand. Logarithmic integrand means that if I integrate over, I get this logarithm of mu. And I call this vacuum integral because it's really looks like a vacuum configuration. It looks like a vacuum configuration. This dot means propagator square. It's a vacuum diagram somehow. At the loop, I have just another thing to add, that is a logarithmic divergent two-point topology, or integrand, or vacuum integrand at the loop. This is the only possibility. At three loop, I have 5 additional possibilities that are all of them giving something that is logarithmic divergent. So these integrands that I'm throwing away correspond to topologies that I write here. This is the one-loop topology. This is the two-loop topology. Those are the 5 three-loop topologies. And those are the divergent scalar, let's say, integrand that I'm throwing away. In case I have tensor integrals, I can show that they can be reduced to this topology plus computable final constant. So those are really the things that I'm throwing away at the end of the day. So they really look like vacuum bubbles that I'm just discarding from the physical spectrum. So in a sense, infinities in this framework are directly put into the vacuum. I'm not putting those infinities in the parameter of the Lagrangian. It's like redefining the vacuum order by order in the perturbation, in the loop expansion. At one loop, I just have to throw away this kind of configuration. At two loop, I have to redefine my vacuum and define my observables by throwing away also this possibility, etc., etc. So what I'm changing order by order is not the Lagrangian, but the vacuum. And what is the price that I pay again to do that? And that I have a dependence in my physical observables on the renormalization scale. That, however, after I fix the theory, if I am dealing with the renormalizable theory, this dependence drops, as it happens also in dimensional regularization. And so, at the end, in renormalizable theories, everything is equivalent to what happens also using any other scheme, of course. But the idea is that I'm not putting infinities in the parameter of the Lagrangian, but just putting them into the vacuum and redefining the vacuum order by order. And this is what actually I'm doing pictorially. I have an integration here, a three-loop integration. And if all the integration momenta go to infinity, this is actually a topology that I get. Now, when all the integration momenta get very large, actually it is irrelevant what is attached to this diagram. So this behaves like a vacuum bubble. And also I have some other configuration where a sub-integration goes to infinity, so it is irrelevant what is attached here in this limit. So I'm also throwing away this infinity. This is related to your question, actually. I'm throwing this because it doesn't take part to the interaction anymore. Somehow it has to be subtracted from the interaction. So, and those I can interpret as vacuum bubble generated by the diagram that I'm actually discarding in order to define the true interaction. I spoke about the finite renormalization that I need to get rid of this logarithm of mu. And I will show you that this framework is such a way that no order-by-order renormalization is actually necessary. And you can also understand this because I'm not speaking about counter terms to add in the Lagrangian. I'm just taking the Lagrangian as it is. I'm not adding counter terms. I'm just throwing away infinities. So I don't need order-by-order counter term Lagrangian. The only thing that I have to do at the end is to fit the parameter of the Lagrangian in terms of observables. And at one loop, as I told you, this is equivalent to dimensional reduction. Dimensional reduction is a dialect of dimensional regularization, where also you have epsilon explicitly appearing in the numerator. You put it to 0 instead of epsilon. But it's a consistent scheme at one loop. In the MS bar scheme, this is the dictionary between FDR and dimensional regularization. So let me speak about this at higher loop, I get the same result, but it's not dimensional regularization in the sense there is no one-to-one correspondence. So it's I don't know what it is. Yeah, but again, I cannot tell you that. At the end, should be a different scheme, but not diagram by diagram. That's what I'm saying. I will give some example in a moment. So let me speak about this finite renormalization that I need. If I have a normalizable quantum field theory, I have a Lagrangian that depends on m parameter. And before I can do a prediction, I have to fix the parameter in the Lagrangian in terms of experimental observables. So I have m equation like this, and then I can extract the parameter as a function of the m experimental observable. And this parameter determined through this experimental observable, I call pi bar. Then if I compute observable number m plus 1, and I compute this at the value computed before, this is a prediction of my quantum field theory, and this doesn't depend on the renormalization scale. Okay, this is, if you like, this is the basis of the renormalization group equation. Physical observable don't depend on the renormalization scale. So, bottom-up approach. I should be able to reproduce the physics of the renormalizable field theories using this approach, and to test that actually everything works okay. The first test I did is reproduce the IBJ anomaly. And it is nice to see that actually the IBJ anomaly is reproduced thanks to these special integrals that I spoke before. So this integral should be interpreted as a normal integral, otherwise it would give you 0, but it should be interpreted in such a way that I should expand this as this mu square was a q square, and then this mu square is 1 over mu square coming from this expansion. So this gives me a finite piece, and this is actually what is causing the anomaly to happen over there. Then I computed in a generic Xi gauge X to gamma gamma. There are 26 diagrams in the generic Xi gauge in the standard model, bosonic-like loop like this, plus all the other particles that I have in the general Xi gauge. Then there are 2 diagrams where I have a fermion flowing here. And this is the amplitude MW, and this gives me the amplitude that I call MF, the fermionic part of it, and those are the relevant scales in the 2 cases. How? No, they're not finite. Yes. No. At the end, of course, there is no divergences, because we know that the result is UV finite, but diagram by diagram you can have divergences. Yes. You see immediately. For example, this diagram alone is divergent, and then if you add the other with the other row, you have simplification, and then it's not. But it's so that should happen not because I know it, but because the calculation should tell me that at the end I get a finite answer.
But wait, the sum of all of them.
The sum. Yes, of course. Oh, this is subtle, because there was a paper a few years ago by Gassmann and Wu that they tried to do the same calculation completely 4-dimensional, and they failed. because there are very delicate issues. Infinite minus infinite is not always equal to 0, even in dimensional regularization. I will tell you. Yeah, I will tell you where this is coming from. Anyway, we perform this calculation, and this is the amplitude is the bosonic part plus the fermionic part, and you get we computing all the diagram. This is the result for the bosonic, and this is the result for the fermionic part. What is difficult to get are those constants 2 and 1, because in the calculation of Gassmann's and Wu, in the 4-dimensional scheme that they were using, they completely missed those constants. So they claim that there was a kind, because without this constant there is the coupling property of this amplitude. So they claim that it was then maybe a better scheme, their scheme, because the decoupling theorem was working there, while in the normal result obtained by dimensional regularization this was not happening. But unfortunately these constants are over there. And you can understand why these constants are over there. The source of these constants is that, as I told you, infinity minus infinity is not always 0. If you would compute this integral in naively, without taking care of this cancellation between numerator and denominator, you would get 0. While now I have to, since this q square is coming from Feynman rules, I also have to continue this to be a q bar. Then I get a kind of S-tag integrals that again is giving a constant piece. And this constant piece is what I need to get this constant right. So it's not enough to perform the calculation in 4 dimensions. Really, you have to regularize your integrals, perform the calculation, and then take the regulator to be 0 at the end. Otherwise, you miss the result. And you have to have a good regulator that fulfills the gauge invariant properties of your theory. Otherwise, you don't get the right result.
It's anomaly like calculations. Is this method calculation, is it easier than the usual method?
I think that is equivalent to dimensional regularization. You know, the Toff-Bellman scheme, except that I know where to put the Q, because
But in the textbooks, one analyzes dependence on the sheets.
no, I'm used, okay, it is equivalent to dimensional regularization, because dimensional regularization is shift invariant. But dimensional regulation has ambiguity, because the result depends where you put the gamma 5 before continuing Q to n dimension. But here it's easy, because once you decide to put the gamma 5 on this vertex, all the rest is automatic. But in dimensional regulation, the same. If you would put gamma 5 here and then perform the calculation, you would get a different sign of the anomaly. But if you decide to put gamma 5 and then go on with the rest, it means that you decide to conserve this electromagnetic current, and this other current is not conserved, but it is an actual current, so you don't care if it is not conserved, at least in pi 0 going to gamma gamma. But once you fix where gamma 5 is, so there you can use shift invariance, because FDR integrals are shift invariant, so it's as easy as dimensional regularization. So, two-loop calculation that we just performed a few weeks ago. So we compute Higgs in gamma gamma, but now adding gluonic correction. So it's two-loop calculation. And there are 12 diagrams, 6 of them here, and also with the arrow going in the other direction. So we computed all the diagrams and all the result. And the important facts, the outcome of this calculation is that, first of all, we got the right result. And we compute the result in the limit m top equal to infinity. And the structure of the result is the one-loop result that doesn't depend on the top mass in this limit, 1 minus alpha strong over pi. So the effect of this gluonic correction is just to add alpha strong over pi to the one-loop amplitude. And another important fact, as I was mentioned before, there is no integral by integral correspondence between dr and FDR. We perform also the same calculation in dimensional regularization in order to understand what we were doing. But really, integral by integral, you get a completely different result. Only at the end you get the right answer. And then while in dr, you have to renormalize the top mass in order to get the right result. There is no need of such a renormalization, at least in the limit m equal to infinity in FDR. And we understand this because you avoid, as I will try to explain you in a moment, spurious epsilon over epsilon term that you have to cure in dimensional regularization through order by order renormalization. And this is what happens. Actually, in dimensional regularization, you have to renormalize the top mass that gives you this contribution. Delta M is the contour term that you would have to add in the Lagrangian in order to renormalize the top mass. So you get extra terms like this. So you have to also do compute diagrams where you have this mass renormalization that happens to be all this kind. So what happens in dimensional regularization is that you get a coefficient of delta M that is of order epsilon times delta M. Delta M is a contour term in dimensional regularization, so it goes like 1 over epsilon. Epsilon is the normal epsilon dimensional regularization. So this gives you a constant term in dimensional regularization. While in FDR, we get 0, the coefficient, times delta M. Delta M is going like logarithm of mu. So actually, the total contribution of this one loop renormalization in a two loop calculation is 0 in DR. Sorry, is 0 in FDR and no 0 in dimensional regularization. So this tells you why all these integrals that we compute in the intermediate state should be different, because the same result is obtained in two different ways. So what about this absence of order by order renormalization that we experience in FDR? I want to tell you, give you a simple QFT example in order to understand why we don't need order by order renormalization in FDR. If you perform a two-loop calculation in dimensional regularization, before you go to two-loop, you have to renormalize your Lagrangian at one loop, and then you can compute two-loop. We don't have to do that. And the reason is clear with this example. Let's imagine that I want to compute the gluon self-energy at one loop. This is what I get in dimensional regularization. I have a tensor structure, and then I have a coefficient pi p square. And in dimensional regularization, this coefficient has the following structure: 1 over epsilon times a coefficient plus the finite part plus epsilon times pi 1. This epsilon goes to 0 when I take epsilon equal to 0, and so this is the pole part. Now let me try to see what happens if I want to square it. If I want to do a two-loop calculation, I would have to square it. But if I square it, I would also get a term that is coming from 1 over epsilon times epsilon. So I would get also a constant part proportional to pi minus 1 multiplied by pi 1. That is not physical, because we know that in the action of squaring this, in order to fulfill all unitarity properties of the theory, should be just pi 0 square. So I cannot allow this kind of term to be present. So then I have to add the contour term in the Lagrangian such that I kill this 1 over epsilon pole. So I add this contour term, and now if I want to perform a two-loop calculation, I have to consider this diagram, the original diagram, plus a contour term. So this gives me this, and the contour term is defined in such a way that I drop the pole. So if I want to perform a full two-loop calculation, I have to consider the original diagram squared plus all possible way of putting this contour term, and this is actually giving me the right result, that is pi 0 square. While in FDR, what I get is that this is directly pi 0, because 1 over epsilon I don't have, because I subtracted from the very beginning at the integral level. So I'm allowed simply to square it, and the result of this is simply already pi square. And I can show that pi 0 is actually equal to pi FDR pi square. So I get exactly the same result as dimensional regularization without the need of adding these contour terms. So the effect of these contour terms that one needs in a loop is always to cure this 1 over epsilon times epsilon terms that sometimes they are not physical, that are taken care, one can take care of them by using this order by order renormalization that it's not needed in FDR. So it's technically it's simpler. So this also tells you something, that in dimensional regularization, if I have two-loop diagram that is actually factorizable 1, that is actually just the product of two one-loop diagrams, I cannot simply take the result to be the multiplication of the two, because each of the two diagrams will have 1 over epsilon pole. Then I get 1 over epsilon times epsilon. So I have to expand one order further in epsilon the integrals in order to get the finite part of this object. While in FDR, in case of factorizable two-loop diagrams, the result is just the product of the one-loop diagram directly. So even from this point of view, this is actually a simpler way of computing relative corrections. So let me briefly speak about the last test that we performed. This is H going to gluon in the m top equal infinity limit. And this is the result that is known since 20 years that we actually reproduced using FDR. The importance of this example is that now there are ultraviolet divergences and also infrared and collinear divergences into the game, and also alpha strong renormalization. This is how this result is obtained in the normal dimensional calculation, dimensional regularization. So it was very interesting to obtain the same result within this four-dimensional framework. So let me explain you better what I'm doing. So this is actually the x going to gluon at one loop. If you take the limit m top equal to infinity, you can shrink this vertex in an effective vertex like this. And then you can write an effective Lagrangian that describes this kind of interactions. So you write these effective interactions, and then this generates this kind of effective Feynman rules. They are three-level Feynman rules that you get integrating out, if you like, the fermions. Okay, the top mass goes to infinity, and you get. So these are actually shrinked fermion loop of the top. And what I'm calculating here are just gluonic correction to this kind of vertices. So x to gluon, you have virtual corrections, but since you have infrared and collinear divergence, you also have to add the real radiation of gluons in order to cure them. And also only the sum of the virtual part plus the real part is infrared safe. So these are the kind of diagrams that I'm considering here, virtual diagrams and real diagrams. The diagrams in red are the only ones that are not zero. This is clear in dimensional regularization, because in dimensional regularization, scaleless integrals are zero, while I'm not sure what, I should check that I'm not using dimensional regularization, so I should see what happens in the case of scaleless integrals in FDR. What happens is scaleless integrals are also zero in FDR. And this is actually by actual computation, by using the definition of FDR integral in this case. You see that this is, for example, a b-point function, a two-point function. And you get the cancellation of logarithm of mu square of ultraviolet origin with the logarithm of mu square of infrared origin. So this is the result, and that if p square equal to 0, you get logarithm of mu square minus logarithm of mu square, so you get 0, exactly as in dimensional regularization. And this treatment should also match with the treatment of the reals that I will speak about in a moment. So this means that all diagrams that are 0 in dimensional regularization, at least in this particular example, are also 0 in FDR because of this property. This I skip. So then the calculation of the virtual part also implies that I compute some integrals that are not UV divergent, but they are just simply collinear or infrared divergent. Like this integral. This integral is the three-point function coming from this triangle that is UV finite, but can be infrared or collinear divergent. So I interpret this in the same way, in a way that is consistent with my FDR integral. So I take the limit mu equal to 0 outside integration, and I take the mu square, the I0 prescription in the propagator seriously. And then this is not actually divergent anymore, in the sense that this mu square also regulates collinear infrared divergences. So I can compute this integral and get this result. I get a double log in mu square. And the virtual part is actually proportional to the real part of this function. So I'm using some regulator for the real part, regulator of the infrared and collinear divergences. I should use a consistent regulator in the real part, because the cancellation between real and virtual happen only by using a consistent regulator in the 2 plus. Dimensional regularization, for example, is a consistent regulator because I can use dimensional regularization for regulating infrared divergences in the virtual part, and I can use dimensional regularization for the real part also, and I get the cancellation of the divergences. So what is that matches my treatment of the infrared divergence in the virtual part, in the real part? One can think a bit on the real part as a cut over two loop diagrams. And actually, what turns out, I have no time to go into details, that what matches the treatment of the infrared divergences in the real part is actually a completely massive phase space integration. I compute the real matrix element square like if everything was massless, and I get expression in terms of Sij, where Sij is just like pi plus pj square. It's just propagators, if you like, square. I express the result in terms of these propagators, and then I integrate this in a fully massive phase space where pi square equal mu square, the same mu square that I'll be using in the virtual part. And then what happens is that I can match, this is just technical details, that I get logarithms of mu square and single log of mu square, and this is the finite expression that I get for the real part. And when I put real and virtual part together, I get this expression. In the real part, I'm actually integrating over the full available phase space. So this is a completely inclusive result. So this is almost what I have to get, because if you remember, that you will not remember the original expression, I don't have this 11/2 in the original expression, but this is actually good because I still have to renormalize alpha strong, and this logarithm is exactly the logarithm that I need in order to renormalize alpha strong. So I need this finite renormalization that I was speaking before. So I can reabsorb this logarithm in the running of alpha, and at the end, this is exactly the right coefficient that I have to have that matches the coefficient of the beta function. So I can now reabsorb this logarithm in the running of alpha, and this is actually the expression that I have to get. So up to now, this shows that everything is consistent with the normal way of doing calculation in dimensional regularization. The first few slides about the non-renormalizable quantum field theory. So let me try to copy what I've done for the renormalizable quantum field theories in the case of non-renormalizable quantum field theories. So what would change? Okay, as I told you, I don't touch the Lagrangian. I'm just throwing away infinities, putting into the vacuum, you name it, what I'm doing with infinities, but just I don't take care of them anymore. So what would happen for theoretical observables is that since now I'm dealing with the non-renormalizable field theories, even after fixing the theory in terms of parameters, if I perform experiment number m+1, there is no guarantee that this doesn't depend on the renormalization scale anymore. So in principle, in non-renormalizable quantum field theory, I would, even after renormalizing, after fixing the theory, I cannot get rid of dependence on this arbitrary mass. So the point is that what are good observables for this Lagrangian of non-renormalizable field theory? For example, at one loop, I can take observable number m+1 that would depend on logarithmically on logarithm of mu, and then observable number 2, another observable that would have a logarithmic dependence like this. I can always cook up combination of those variables such a way this logarithm of mu r disappears. So in this case, I call this particular combination of observable a good prediction of my non-renormalizable quantum field theories. I cook up, I cannot predict all observable, but just observables where this dependence on this logarithm actually drops. But I can take this reasoning to the extreme, and if you think what I've done here is just kind of fixing the logarithm of mu r from experiment n+2 and plug in the result in experiment n+1. This is what I've done. So actually, what I can think of in principle is just to add just one additional measurement in order to fix logarithm of mu and putting this to observable n+2, and then this would be actually a prediction of my theory. Different stated, just adding one more measurement with respect to the measurement that I need in order to fix the theory, I can actually fix completely computing any observables just with one additional measurement independently on the number of loop I'm considering. So in this sense, predictivity is restored in the infinite loop limit. So important facts for this approach. It is crucial that the original cutoff mu equal to 0 is traded with an adjustable scale mu r. That is what at the end I'm fitting. This is something that is important. One has to assume that the solution, when I fit this mu r, still allow a perturbative treatment if I want to insist with perturbation theory. So if G is the coupling constant of the theory, G squared times this log should be less than 1 if I want to have perturbativity. I have to say that I just put this in words. I didn't verify this kind of approach in practice, and this needs more investigation. And the physical meaning of this extra measurement, if you like, is completely disentangling the UV effects from my observable. It's like ignoring the UV completion of the theory. If you like, lambda, this Lagrangian non-renormalizable is still describing effective theory, but somehow I can parameterize my ignorance about the UV completion with this extra measurement. And that's it. This is what I've done. I gave you a new interpretation of the renormalization procedure by introducing a new kind of integral. The divergences are directly subtracted at the level of the integrand, and this corresponds to a vacuum redefinition order by order without touching the Lagrangian. I could reproduce actually any result of perturbative renormalizable quantum field theories can be reproduced because this integral fulfills all good properties that one wants to have, that it has in order to perform actual calculation. It is postulated that non-renormalizable quantum field theory can be dealt with just one additional measurement, and without modifying the original Lagrangian, I can give some meaning to the theory. So in this sense, the theory can be predictive. So in a sense, the focus is moved from the occurrence of the UV infinities from the consistency of the quantum field theory at hand. I'm not forced to add extra interactions in order to, because there are UV infinities. I could change the Lagrangian because the new Lagrangian fits better the data if I add new interaction, but there is no excuse in changing the Lagrangian because I have UV infinities to absorb in the new terms that I added to the Lagrangian. So I'm separating somehow the two issues. And then everything is in 4 dimensions, so this enhances the potential of numerical approaches if I have complicated loop calculation. I'm thinking essentially of 2 loop and beyond calculation, but this is still a work in progress. But I anyway find interesting the fact that everything could be formulated in 4 dimensions without having to go in D dimension. This is it. Thanks for your attention. Well, this year I'm going to give a course on this, so I'm tempted by the idea, but well, maybe not.
So you think it's possible to completely not mention dimensional avoid?
I think so. I think this is doable, but I wouldn't do that because the student have to know what dimensional. I think it would be easier because whenever I introduce dimensional regularization during my classes, everybody is protesting because they say, why are we really living in the dimension, etc., etc. So this would avoid completely this problem.
At the level of calculations, for example, the textbook way of calculating beta functions, as we discussed.
Yes.
I
Well, to compute the beta function, as we were discussing, maybe I would just, take what I'm throwing away, but this would maybe something similar to what is done in dimensional regularization. So I don't know. I have to think about beta function.
They appear for the ultra strong renormalization next order, that you get an extra term could it correspond to this beta function renormalization?
Look, I will have to compute the beta function at 2 loop because for my next calculation. So I don't know what to tell you about beta function more than what I told you. I think that I have some idea how to compute this, but I should look into detail before I can answer in a proper way to your question. It will be interesting to see the scheme because at 1 loop I know what it is. But at 2 loop, I don't know in QCD if this corresponds to some known scheme in QCD or if there is some constant floating around. This I don't know. By actual calculation, I should prove it. And maybe by doing the calculation, I could immediately see why this scheme is actually equivalent. But I don't have an answer at the moment.
For your graduate students, would you explain us the meaning of infinities?
I would tell you that infinities are just quantum fluctuation of the vacuum that I have to subtract from my interaction. This would be my physical interpretation of the infinities. In some theories, you completely can, they are so universal that you don't have any trace of them in the physical observables. In non-renormalizable field theories, you need one extra measurement in order to completely factorize this from the physical spectrum. This is my way, this would be my way of explaining this. But they are unphysical. They are unphysical because they correspond to 2 points going so close that you need an infinite energy to do it. That is impossible.
So you can capture all that divergences?
Yes. Quadratic, polynomial, doesn't really matter. Everything that's divergent, I subtract. And actually, if they are more divergent, the more divergent they are, the better they are, because they are always proportional to mu to some power, so they go away. So what really kills you, kills you. I mean, you have to pay a price only for the logarithmic divergences. This is the only thing that you cannot actually separate without paying any price. That is interesting in a sense, but...
In this sense, it's even better than dimensional regularization.
Well, yes, thanks. Of course. Now, look, well, I was thinking about the fact that you don't have any problem if you have these polynomial divergences in this framework, because unless you have really a particle with a mass of 200 TeV that couples, then if you have an integral with such a particle floating, this is not proportional to mu to some power, but it's proportional to this mass to some power. So you cannot neglect physical particles in this argument of quadratic divergences. So in this sense, this tells you that it's really unnatural to have very heavy particles, because it's much more natural to have a continuum, because this continuum with this, at least in this framework, it's you can neglect polynomially divergent integrals. While if you really have actual masses, this would give you a contribution that is really proportional to the mass of the particle to some power. So, and this would cause a hierarchy problem. Well, if you don't have any particle, if you have a big desert, it's much more natural in the framework that having some particle that try to cure hierarchy problem. But this is completely, my personal opinion. To gravity? Ask him. Well, look, no, I mean, there is nothing special about gravity. Look, in principle, you can also use the normal approach to any effective field theory. You can put contour terms, as many as you like, and then to put the finite part of this extra interaction that you use in order to solve infinity to be 0. Then you just put a contour term Lagrangian where you just have the 1 over epsilon powers in order to cure the UV divergences, and then nothing else. Then you don't have to fit this constant term, the finite part, with any extra measurement. And then you would probably end up with something similar to what I'm saying. So this would probably is equivalent to normal way of dealing with effective field theories have said that I'm just forcing all the finite part of the term that I need in order to normalize it to be 0. So then I don't have to measure anything. In my way of looking at it, adding the final part different from 0 is equivalent to changing the theory. So, but if you say that the theory from the very beginning has all the interaction, okay, there is no difference. I'm just saying that somehow if you put some finite part of this contour term to be non-zero, you are just moving in a space of theories and just choosing one theory on another theory. But what I wanted to do is just not to touch the Lagrangian, assume that any Lagrangian that I have is self-consistent, and to see what I can do with that Lagrangian without the need of changing it. This is my philosophy.
How do you know consistent or somewhat consistent? What criteria do you consistent?
Well, it is inconsistent if it doesn't describe the data. So maybe you really have to add some more interaction because it describes better the data. This is driven by experiment in a sense, more than by your prejudice about the theory.
How could you deal with scaling variant theories in your intervals? There are no scale at all. How could you split it between?
If you don't have scale at all, you leave it as it is. In some cases, you get 0 because you don't split it. If you don't have anything to split, you don't split. You leave it as it is. You don't do anything.
Usually, if I remember correctly, you said you throw away the parts that don't depend on the scale.
Okay, if there are no scales and this is UV divergent, you throw it away directly without doing anything.
It's fine at all.
It is finite, okay, you do it.